In this lecture, I'm going to be explaining another approach for future learning, and we use contrastive proposal encoding. And the application is just in the focus of object detection. And the model is called FSCE. So I'm going to be focusing on this paper in 2021. And this is a positive sample. Emerging interests have been brought to recognize previously unseen objects given very few training examples, known as few-shot object detection. Recent researches demonstrate that good feature embedding is the key to reach favorable few-shot learning performance. We observe object proposals with different intersection of union scores are analogous to intra-image augmentation used in contrastive approaches, and we exploit this analogy and incorporate supervised contrastive learning to achieve more robust objects representation in few-shot object detection. We present few-shot object detection via contrastive proposal embedding, a simple yet effective approach to learning contrastive aware object proposal encodings that facilitate the classification of detected objects. We notice the degradation of average precision for rare objects mainly comes from misclassifying novel instances as confusable classes. So they are not confusable classes, they are novel instances. And we ease the misclassification issue by promoting instance-level intra-class compactness and inter-class variance via our contrastive proposal encoding laws. This is conceptualization of our contrastive object proposals encoding. So we introduce a score function which measures the semantic similarity between region proposals. Positive proposals refer to region proposals from same category or the same object. And the negative proposals refer to proposals from different categories. And we encourage the object encodings to have the property that the score of, the anchor and positive should be more than the anchor and negative sample. And we find that in fine-tuning based few-shot object detection, classification is more error-prone than localization. So classification is more error-prone. But in the fine-tuning, RPN is able to make good enough foreground proposals for novel instances. This is an overview of the proposed method. They jointly fine-tune FPN pathway and RPN while fixing the backbone. So this backbone is fixed, which is ResNet 101, and they jointly train it. What we design a contrastive objective to maximize the within category agreement and cross-category disagreements. So this is contrastive proposal encoding. So think about two-stage fine-tuning. Original TFA only fine-tunes the last two fully connected layers, box classifier and box regressor with novel data. The rest of the structures are frozen and taken as fixed feature extractor. This could be viewed as an approach to counter the overfitting of limited novel data. However, it is counterintuitive that feature pyramid network RPN, especially the ROI feature extractor, which contains semantic information learned from base classes only could be transferred directly to novel classes without any form of training. In two-stage detection frameworks, RPN takes backbone feature maps as inputs and generates region proposals. ROI head then classifies each region proposal and regresses a bounding box if it is predicted to contain an object. In faster RCNN pipeline, ROI head feature extractor first pulls the region proposal to fixed size and then encodes them as vector embedding. To incorporate contrastive representation into this framework, we introduce a contrastive branch to the primary ROI head, and it is parallel to the classification and regression branches. The ROI feature vector contains post-ReLU activation, thus is truncated at 0. So the similarity between the two proposals embedding cannot be measured directly. Therefore, the contrastive branch applies a one-layer multi-layer perceptron head with negligible cost to encode the ROI feature to contrastive feature. So we measure similarity scores between object proposal on the MLP head and optimize a contrastive objective to maximize the agreement between the object proposal from the same category and promote the distinctiveness of proposals from different categories. And we adopt a cosine similarity based on bounding box classifier, where the logic to predict the ith instance as the jth class can be computed like this. So for a mini batch of n ROI box features, so Zi is contrastive head encoded ROI feature for the ith region proposal. This is the ith region proposal. And UI denotes the intersection over union score with matched ground truth bounding box, and Y sub I denotes the label of the ground truth. And of course, tau is just the hyperparameter temperature that we know. N is number of proposals with the same label as Y sub I. And we also use the normalized feature because the dot product and cosine similarity, it measures cosine similarity between the ith and jth proposal, and the optimization of above loss function increases the instance level similarity between object proposals with the same label and spaces proposals with different labels apart in the projection space. Unlike image classification, where semantic information comes from the entire image, classification signals in detection come from region proposals. And we propose to use an IOU threshold to assure the consistency of proposals that are used to be contrasted, with the consideration that low IOU proposals deviate too much from the center of regressed objects. So there is a reweighting function here, and this F controls the consistency of proposals. This is the conceptual TSNE and TSNE visualization of object proposal embedding. So this TSNE, you see that it shows the proposal encoding from randomly selected 200 Pascal images. And the right panel shows bad cases.